Yeah, I think we might get started.
Okay, let's get started. So welcome everyone to the CMKL Talk Series 2020. CMKL is established as a collaboration between Carnegie Mellon CMKL Thailand and KMITL. We aim to expand research and education in the areas of information, computing, and autonomous technologies. Today, we're so excited to have Dr. Tze Meng Lo, Assistant Research Professor in Electrical and Computer Engineering at Carnegie Mellon University, to give us a talk on the topic of performance at the core of AI and data analytics. So at the end of the presentation, we'll have a Q&A session. So please type your question in the chat box, or you can also unmute yourself at the end of the presentation to ask questions. So now I'll let Dr. Tze Meng Lo take over the talk.
Right. Hello, everybody. Thank you for inviting me to this talk series. Right, so today I want to talk, as the title suggests, is about performance that drives the AI and the data analytics that we want to do today. Right, so the main idea is this. Today we live in a world of data, and the data comes from many different sources. Could be from our Internet of Things, could be from smart city, they could be also images we collected and we want to process those data, either to figure out connections between related items or disconnected items, or to even figure out things like whether there's a person in the picture, right? We live in a world of data, we want to process the data, and we want to do it fast. And as the amount of data increases, we want to do it more and more often, faster and faster, to make sense of the increasing amount of data. Right? So a traditional approach is, well, if we have more and more data, let's just buy more and more hardware resources. And in fact, that's what we are doing even up to today, right? New processors are being introduced. Each processor traditionally is only one core. Now we can buy machines that have hundreds of cores sitting on them. We have new accelerators that are being designed and built every day, specialized for machine learning and graph analytics and different other purposes. Right. Similarly, we have GPUs. Traditionally, they have been used for graphics, but nowadays they are used for computing, they're used for Bitcoin mining, they're used for many other purposes, right? When we have data, we will always buy or procure a latest processor, a more powerful machine to process our data. And if we take that to the extreme, today we have cloud services. If you have a lot of data, you have the cloud services, you procure what you need from the cloud service. Right? This is a very hardware-centric approach. The problem with this is, well, you bought the hardware, you still need to make sure that the code you want to run is ported appropriately from one machine to the new machine you bought, right? And for that reason, we need to talk about performance portability, right? It's not just about taking the code and then using a compiler and run the compiler and create a code for the new machine, right? Very often, when you buy a new machine, in order to get the most out of your machine, right, you often have to rewrite your code, often have to retune your code such that you are maximizing the use of the new machine and maximizing the capability of that new machine. After all, it is as if you bought a sports car, that can go very fast, but if you're only driving in first gear, then you're not using the use of maximizing the use of that sports car, right? Same thing for hardware. You bought a new machine, you want to maximize this use. And because of that, a lot of tuning, optimization has to be done. And often these are done manually. Now, traditionally, that's not a problem. You can always do it for one machine because machines come out not as frequently as they come out today. Secondly, the types of machine is usually about the same. You have one CPU, you move to a different CPU. Whereas today, with the large variety of architectures and platforms you can compute on, this manual effort, this heroic effort of optimizing one code for a particular architecture no longer is scalable. We need to find better ways of doing it. And it's not just about the computing architecture platform, right? when we have new machines, we want to not only compute old problems, we want to find new problems that we can leverage this new machine to solve. So as the architecture changes, as the architecture improves, we have new applications that are coming. We have new ideas on how we can better analyze our data. Right. For this reason, again, you have to repeat the analyzing, the optimizing effort. Right. So now, it sounds very bad. It's not so bad because we actually have a lot of tools today that help us get decently fast code on one machine when we move to another machine, right? The problem with these tools is that while they are very good for coming up with fast implementation quickly, they provide very little insights into why the implementation is either good or bad, right? They just give you a result, and often it's better than what a naive programmer would implement. And so therefore it's often faster than what can be produced manually. But why does it perform better? Why does it not perform better? Are we maximizing the use of the hardware that we want to, right? These black box tools provide very little insight. And if you want to understand how you can take the same ideas and use it in a different application or use it in a different machine, then these tools are not very useful in that context. But in terms of getting performance, they are often very useful. Right. Just to illustrate what I mean by performance portability, let's talk about CNNs, right? Convolution neural nets. And it's a very common image processing deep learning network. Even within the word CNN itself, you see that there are many, many different networks. Here, I show just 3 very old networks by this time, which is AlexNet, VGG, and GoogleNet, right? These are 3 different CNNs, and within each network itself, there are many different convolution layers. Each of them are configured slightly differently. They have different filter size, they have different channel size, they have different images, and so on and so forth. The parameters that configure that network, that particular convolution layer in the network changes drastically. So, and here I only showed 3. Today, there are way more CNNs out there, and they are often customized for the particular application that they are designed for, right? Beyond the networks themselves and the different convolution layers, here I also show each row representing a different machine that you can purchase off the market. So one's an Intel Haswell, one's an ARM core, one's an AMD CPU, right? So you have, not only do you have the complexity of having to manage different applications, in this case, different CNNs. The CNNs themselves are configured very differently. Now you have the problem of how do you go from an Intel machine to an ARM machine to an AMD machine as well, right? Each of them themselves, the hardware is very different. So the Intel Haswell is a 4-core machine. The ARM is a 2-core machine that uses specific instruction data sets. And then the AMD, even though it's 4 cores, if you're doing certain things, is the equivalent of 2 cores and so on and so forth. So the main message here is portability is important. And even for a single problem like CNN, we already see many, many differences, let alone the many different problems we want to solve today when it comes to AI and data analytics, right? So getting good performance is important and essential. Now, to further, so many of you will say, well, it doesn't matter, right? I'm going to use a optimized library. And yes, you should. But very often, the optimized library, in order to use them, a lot of inefficiencies are being introduced in the application itself. To illustrate this, I'm going to use an example called the deep learning recommendation model. Now, it is a very customizable deep learning based model for doing a recommendation. So think of Netflix, Amazon, they will recommend you things. So deep learning model is along the same line. It helps predict what a user would like to, what ads you should serve to a consumer, what product should you recommend to a particular consumer. And this is a model that's introduced about a year ago and is part of the machine learning performance benchmark suite. It was introduced by Facebook in 2019, right? Why is it customizable? Well, the deep learning, the DLRM model essentially comprises of 4 major components, right? There's a top MLP, bottom MLP, some sparse embedding, and a mixing layer. It's always in these 4 configurations, but depending on the recommendation you want to do and the factors you want to consider, the number of sparse embeddings may change, the depth, the number of MLP layers may change, and so on and so forth. But it's customizable because you can change all these parameters. But the structure of the DLRM remains fixed. So to illustrate the inefficiency that can be introduced, specifically, we are going to focus on the mixing and interaction layer, right? So in the mixing and interaction layer, it's actually one of the smallest component in terms of time it takes to execute. But if you look within the layer itself, you see that you start off with data in a particular form. You need to do a reshape to transform or repack the data into a different form. You then need to transpose it, and then you do a small matrix multiply. In fact, it's a batch matrix multiply. And once you're done with that, then you have to do more data movement to concatenate it together, right? Now, this batch matrix multiply is a call to a high performance library, right? So the implementation is running well. But in order to call that library, you see that there's a lot of data movement that has to happen. These are all time that is spent just moving data around, not doing actual computation, right? So not only does it take up time, but it also takes up space because you start off with your input data in one format. You have to create a buffer, repack the data into a different format, and each transposition, each data movement, each data packing requires both time and space. So to illustrate how much time and space it is, let's look at the different components of the execution time for the interaction layer. Here, I show the 4 different stages: the reshape, the transpose, the batch matrix multiply, and the concatenate at the end of the operation as a percentage of the total execution time. Here, I also show 2 different configurations for the DLRM running on the CPU, and 2 configurations, the same 2 configurations running on the GPU, right? And if you look at this, the only computation time that is taken is the dark blue bars, right? So in the very best case, you're spending about 70% of the time doing computation. You're still wasting about 30% of your time doing data movement. In the worst case, on the CPU, you're only spending about 30% of the time doing actual work. The remaining 70% of the time, what you're doing is you're actually moving data around, right? Not doing actual work. And again, this is just based on the amount of time. There's also the space that is required to actually hold the entire data set itself, all right? So yes, using library is great and you should use it, but we need to be wary of what are the hidden costs when we write our code using these libraries. And very often this packing and data movement are often not factored into our thought process when we implement our applications using the libraries. So what can we do? The key questions we want to address, at least today in this talk, is how do we capture knowledge about performance? And if we can capture the knowledge about performance, in the sense that how do we capture knowledge about how we can get the maximum performance out of any given platform, then the next question we want to ask is, once we have this knowledge, how do we then apply it to different applications that may be very different from what we are currently working on, and port it to different architectures, like the DLRM model. Can we take something we learn about the CPU and then use the same ideas and put it on the GPU, right? So those are the questions we want to explore and answer in this talk. So our approach is to recognize that, hey, many of the software optimizations that we do today really is about targeting hardware features. So for example, I show here on the right a diagram of the loops surrounding a matrix multiplication that is written in a high performance manner, right? And if you observe the loops, what we realize is the loops are designed in a particular way such that the data is moved through the memory hierarchy, basically moving it through from main memory all the way through your L3, L2, L1 cache, all the way into the registers where the computation is happening. The loops are designed in such a way that they keep data in a particular level of cache. So in this case, this magenta chunk of the B matrix is sitting in your L3 cache. They're designed in such a way that the data movement is efficient. The data movement are keeping specific pieces of the different matrices in different levels of the memory hierarchy. So what I'm saying is that the software optimizations really are designed based on the hardware features that's available on a particular platform. Now, if we recognize that, then that suggests that we potentially can capture this hardware-software interaction with analytical models. So these analytical models, essentially what they would do is they will figure out which software parameter, which values you set in the software are used and are determined based on the available hardware features. And we'll go through a couple of examples later, but the whole idea is that the analytical models tie your software parameters, the values of your software parameters, to the available hardware features. And when the architecture changes, the hardware feature changes, the model will then inform you whether you should change your parameters or you can keep them as the same, right? So we want to build this analytical model based on the available hardware features for a particular problem. And when hardware changes, when the configuration of the application changes, we know which parameters we need to tweak, or if necessary, rewrite or choose a different algorithm, because what used to be true on one platform no longer is true on the second platform, right? But beyond changing, it also tells us what we don't need to do. Going from one architecture to a different architecture, hey, maybe the hardware features that are required for this particular application doesn't involve the new capabilities of this new hardware. So therefore the code never had to change, right? It also suggests that you may not want to buy that new hardware because it doesn't benefit your work as well, right? So there are many users of this analytical models, but let's look at how we can build such analytical models. Right, so architectures or hardware really are designed to work in a particular manner. They have a prescribed way of doing things, and data that is, or computation that's presented to the hardware in a particular manner often works better if you present it to the hardware in the order in which the hardware was designed to work. So if, again, using the car analogy, the car is optimized to go forward, but sure, you can do reverse, but typically reversing, you're not as efficient as going forward, right? So similarly, hardware are designed to work in a particular manner. We want to write our code to best target the hardware capabilities. So some examples of it includes designing your code such that your functional units, the hardware components that actually do the actual computation, they are fully utilized, right? If they are not utilized, you're wasting resources, they're sitting there being idle. So you want to design your code such that as many of these functional units, these computational units are utilized fully in order to get good performance. That's on the computation side. When it comes to the memory and data movement, which we talked about briefly, the memory hierarchy is also designed in a particular ways. And because of that, this imposes certain constraints on what and how you can move data efficiently through the memory hierarchy, right? So again, the whole idea is that hardware are designed in a particular manner. We want to exploit this. We want to exploit our knowledge of how this works and then design our code so that we do what the hardware is best at doing. So to give a very simple example, now, let's talk about the functional units. In a particular piece of hardware, there are often many functional units or ALUs that are available for computing, right? In this case, I've highlighted 2 units specifically for doing floating point fuse multiply add. Basically, it's a single instruction that does both a multiplication and an addition all at the same time. Now, if you focus on these 2 units, then there are three parameters in terms of the hardware that we need to be aware of. Number 1, how many units are there? Right. Clearly, if you have 2, then you should be doing twice as much work as what if you had only 1 functional unit. Number 2, how long does each instruction take? This often translates to how many independent pieces of work that you need to identify in order to make sure that you can hide the cost of that instruction. And lastly, for each instruction, how many outputs can you compute? If you multiply all these 3 values together, what you end up with is a hardware-based constraint that says, in order for the floating point fuse multiply add functional units to work efficiently, then you need that amount of independent FMA instructions, which means those instructions can be computed in any order. They do not depend on the results of any of the other instructions within this amount of instructions, right? So they need to be completely independent and can be executed. And that's the minimum the hardware needs to perform efficiently, right? So that's a hardware constraint. So let's look at how this hardware constraint changes the way we do our computation. And to illustrate that, we're going to look at matrix-matrix multiply. So for those who are familiar, you're taking a matrix-matrix multiply is just taking a matrix multiplied by a B matrix to compute a C matrix. And the typical way we learn in class is actually you take a row of A, a column of B, you multiply them together, and then you compute a single output of C. Now, if you do it that way, notice that there is a dependency between the multiplications, right? You have to perform the first multiplication, add it to C, before you can proceed with the second pair of multiplication and addition. So you always have to wait for something to be done before you can do the previous instructions to be completed before you can do your addition, right? So those are not independent instructions. Instead, in many high performance matrix-matrix multiply routine, what you see is that you end up with a implementation that's based on the outer product. So the outer product, as shown in the slide, is you have a column of A, not a row, but a column of A multiplied with a row of B. If you do an outer product, then what you will realize is that for every output here, MR by NR output of your output matrix, all the elements, all MR times NR operations can be done independently, right? All you need to do is take the corresponding element of A and B and just multiply them together, right? So the multiplication all can happen independently, and because they are summing to different output values, the sums can all happen independently as well, right? In other words, the reason why the outer product is chosen is because you have MR times NR independent operations. Now this is fantastic, right? Because the hardware requires independent instructions. There are MR times NR independent operations. So now we can put a model together and say, hey, on the software side, you have two parameter values that you can control, MR times NR. On the hardware side, you have the number of functional units, its latency, and how many outputs you get. The number of the software, on the software side, you need to have at least the minimum amount of independent instruction required by the hardware. If you do not have that, then the hardware is not working as efficiently as possible. This forces us on the software side to actually write our code in such a way to actually ensure that this inequality remains true. Now, there are many other constraints that the hardware places, but at least this is one additional constraint that we know when we write our implementation, we need to pay attention to these two parameters. And as we go from one architecture to a different architecture, the number of functional units may change, the latency may change, the size, the number of outputs may change. All these changes impact our choice of software parameters as well. And when we go to a new architecture, we have more functional units, we know how to change the software parameters accordingly. All right? Now, that's a very simple example, but let's talk about DLRM again. Now, remember the whole point of the interaction layer, or the reason why we talk about the interaction layer in DLRM, is the fact that we want to potentially get rid of all the unnecessary data movement and just spend most of the time doing computation. And to do that, we first need to consider things like, hey, you have your data is for a single matrix multiply at the end that you want to perform is actually distributed across different arrays, and we do packing is to make sure that data is stored contiguously, right? So if we know that the things are, these are the two things we know about our problem. In order to map this to the hardware, we first need to know what the hardware we are looking at. And this requires us to talk a bit about caches, right? And this is a brief recap. So caches today are mainly set associative. And what this means is that there's a limited number of different distinct arrays you can load into your cache. Here I show an 8-way set associative cache. And because there are only 8 ways, if you load 8 different arrays that are mapped to the same set, even though the array may be very small and most of your cache is empty, this would fill up the entire set in the cache. And the implication of that is when you add a 9th array that is also mapped to the same set, this additional 9th array will create a conflict, causing cache conflict, causing cache misses, and so on and so forth, right? And this happens regardless of whether your cache is full or not. Because there are only 8 slots that you can put your arrays into, if they all happen to map in the same slots, you know that the 9th array will create cache eviction, will create cache misses. All right? So how do we use that to design a model? Well, remember, the input arrays for DLRM are disjoint and they do different computation. And if we are given an 8-way set associative cache, then that's fine because I can load each array into 3 of the 8 ways. And because I can load the entire array, I can do my matrix multiply without a problem, right? There's plenty of space in the 8 ways to hold the data required to do the matrix multiply, even though they are disjoint array. However, what if we have more input arrays? Instead of 3, let's assume that we have 6 arrays. Well, in this case, you would want to do the same thing. But if you look at this particular block, this particular 3x3 blocks that I've highlighted in the output, what you realize is that the inputs required to compute that is actually all of different color, which means they come from, instead of 3, but 6 different arrays. So the total amount of arrays required to be loaded in your cache before your computation can happen is actually m plus n, and then you have one more because you actually have to write out the output to a different array itself, right? So what I'm saying is that looking at the computation and knowing how many arrays we have, here we know that if I have 6 arrays, if I have 6 arrays and a quadrant can use up to 6 8 ways, this is the best I can do to put data into my cache, right? Because I have the 6 ways required to hold the 6 different arrays. I have 1 for my output. I have no other space to hold any other new arrays, right? More generally, now we talk about a specific case. Now we can talk about a specific case. And if you, more generally, instead of 8 ways, if you have W ways, and you know that the total arrays you require to fit into the cache is this, then you can roughly compute that, hey, you want to have W minus 1 over 2 approximately number of ways, right? Because 2m plus n is W minus 1, right? So now we have a model that says, tell me how many ways do you have in your cache? That informs me how big my tau of my output needs to be, and therefore I can tune my software for that particular architecture using a hardware parameter. So we took the hardware parameters, passed it through the model, and then came up with software parameters that should work well for that particular architecture, right? And if we do that, the short answer is yes, indeed, you can get good performance. Here, we show our implementation using those same ideas compared to the Pytorch version. And here, what you see is, hey, all the non-dark blue blocks have been eliminated. Exactly what we wanted. And the reason is we never needed to pack the data in order to call a function. We just wrote the function ourselves. In addition, because we are writing the function ourselves, we were also able to eliminate some of the more complicated, more expensive operations that may be incurred by the default implementations. All right? Should you do this all yourself? No, but at least you should be aware of it so that when you have to write code, you are considering it. Now, that was the overall execution time results. Yes, we got rid of all the data movement and we got better. So how well does the model how well does the model work, right? The model, so we tested the model. We ran for different problem sizes, for different machines with different associativity and things like that. And based on the model, you should get m approximately equals to n equals to 3. And if you look at this plot on the different architectures, 3 is the place where almost all the implementations got the best performance. Now, I said most because there's one exception here, which is the Ice Lake machine, the red bar, that was supposed to be best at 5 based on the model. Well, in this plot, it's the second best, not the best. And one of the reasons we suspect we are seeing this performance dip is because the number of registers that you have on that machine is insufficient to hold a 5 by 5 matrix. And so because of that, you start spilling into you cannot hold it in register, so you start writing to memory instead. And so because of that, you start to see a drop in performance. But nonetheless, the model is pretty accurate in the sense that it's not the best, but it's the second best, right? So yeah, the model does apply not only to one architecture, but to many different architectures across different generations of CPUs as well, and across different vendors' CPU. Right. We've talked about DLRM. We've talked a lot about DLRM. The question is, how general is the approach of using analytical models and things like that? And yeah, we've designed models for matrix multiply and DLRM. How do we use them for different applications? And the answer is yes, they do apply. And that is because a lot of the knowledge we have when it comes to performance are actually organized into discrete application domains. So you have dense linear algebra being one of them, signal processing, sparse linear algebra, and so on and so forth. Right, I just wrote 4, but there are only a couple. There are quite a number that have already been identified, right? And in the software world, the traditional way, if you're not dealing with the models, each of these domains have their own code generator, they have their own libraries, they have their own packages, right? So we already are designing things not just for one application, but we often do it for a class of applications. So for example, if you just look at dense linear algebra or matrix multiply, you see that there are many different applications that all classify under matrix multiply. The main thing about this is the access patterns are the same. The only difference is what you do once you brought the data into the functional units. In some cases, you're doing logical operation, AND, NOTs, XOR, and so on and so forth. In other cases, you're doing, instead of fuse, multiply, add, you're doing subtraction, multiplications, and so on and so forth. Right? All these, the access pattern are the same. The only difference is instead of doing multiply and add, you're doing something else. So because of that, the model really applies, because the model says what functional units and then how many functional units. So if you are doing a different problem, it's just a matter of choosing a different functional unit to customize the model for that particular application. Right. To illustrate further, there are many other domains. For example, when in the domain of data analytics and graph analysis, you have things like the GraphBLAS, which is a community effort where you describe graphs using their adjacency matrix, and then you write graph algorithms in the language of linear algebra. So this, again, is an idea that, hey, the community has said that these two are the same thing. Let's use the knowledge from sparse linear algebra to solve graphs as well. So again, if you design models for one domain, then that entire domain benefits from the model that you have designed. Beyond application computation and things like that, there's a lot of packing and intermediate layout that are performed in many different applications. In matrix multiply, the colored arrows show that even within matrix multiply, you have to do intermediate packing and and storing them into intermediate layout. Direct convolutions, fast Fourier transform, intermediate layouts are required in order to get performance. And once you have intermediate layout, you have to talk about how do you get data from one layout to those layouts. And then again, the memory hierarchy, the number of ways, all comes into play. Right. Again, to show a slightly different example, when we are working with a large multi-dimensional FFTs, which are known to be memory bound, what we would like to do is to do double buffering with hyperthreads. Now, that's the scenario. Basically, you have multiple threads all working simultaneously. The threads that are highlighted in red are executing or computing on the red and green buffer. Right, but notice that T1 on the two different, T1 and T3s, we are two separate threads on different cores, are sitting idle. And it makes sense in the traditional computation because it's memory bound. Most of the time you're waiting for data to come in from main memory. So what we say instead is, why not use those threads to bring data faster? So rather than reading from main memory, why not let's pack the data required into the cache so that the RAID threads can access the computation, the data a lot faster. It's a good idea until you realize that, hey, the caches are shared. So it means that the RAID thread and the blue thread are using the same resource. And if you are not careful with how we utilize the cache, they may kick each other's data out of the cache. So you're negating the effect and creating more problems for yourself if you don't do it carefully, right? But if you look at it abstractly, it's just a matter of splitting caches amongst into different disjoint arrays. And then you're not only applying it to the L1 cache, but into all levels of the memory hierarchy. And therefore the same idea, how many arrays can I bring in? How much data should I use? How many ways can I afford to dedicate for each block of memory, right? The same idea applies, the same principle applies, and very often when it comes to packing, the same model applies as well. And if you do that correctly, not surprisingly, if 100% is the peak theoretical bandwidth that is achievable, the leading libraries such as FFTW and MKL for doing multi-dimensional FFT are getting between 30+ to 40%. But with our implementation, you can get between 80 to 90% of the theoretical peak of the machine, right? So again, the hardware tells us what needs to be done. How do we need to write the code in order to get performance? And if you follow the constraints provided by the hardware, very often you can write code that is often a lot higher performance. Right, a quick summary. I noticed that there's a lot of chat as well. So the main thing is portability is important today, and it's more important today than ever before because we have many new applications and we have many different new architectures. We need to move our code from one architecture to a different architecture quickly and efficiently, because otherwise, why are we moving to architecture if we are not getting improvement in performance? Right. That's why performance portability is even more important today. And our approach, at least the approach we talk about today, is to use analytical models to design software-hardware interaction, right? And the whole idea is that hardware are designed to work in a particular way. So let's use that as a constraint on how we should write our software. And then use the model then guides us in how we should tune our software when we change the different hardware. More importantly is that rather than a black box library, these models actually help us preserve the knowledge about performance. How do we get good performance across different architectures and different applications? All right. And with that, that's the end of my talk. I'll be happy to answer the questions in chat. And if you have any more questions, please feel free to ask or answer.
Okay, I can read the questions from our participant for you.
Mhm.
So the first question are there any drawbacks of using runtime models like TensorRT instead of TensorFlow or Pytorch? I'm not sure how to pronounce that.
Right. So if you're using TensorFlow, you're using Pytorch and TensorRT, they are all based on expert implementation. So a lot of the libraries they are calling are already highly optimized. So whether there's a drawback in using one over the other, it really depends on the application you're trying to perform. It really depends on what you want to do, right? Sometimes the problem is not with the library itself, but the way we use the library, because we are using a function that may not be optimized for a particular library, right? Implementing a full library takes time and effort, right? So if we are using one where the developers of those libraries and runtime systems have not gotten to it, then you're not going to get good performance when it comes to that, right? And those are the cases, maybe sometimes you want to write it yourself, right? There's no I want to emphasize, if you choose a good library, there are no drawbacks, and that's the first thing you should try. However, depending on the application, so for example, if you want to put DLRM onto a resource constrained device, you want to put it on an edge device that has very little memory, then the packing routines and things like that that you introduce that were not a problem on the CPU or even on the GPU may now become a problem. So you need to be aware of, when you write your code, what is actually happening, and then be able to decide for yourself when you need to leave the standard packages and either write your own or find a different package that's optimized for your particular application and problem at that time.
Okay. Yes, and the second questions are second question is, what are your views on training deep learning models using the current state-of-the-art quantum devices?
So this is something I'm not very familiar with, and especially when keeping updated with the state-of-the-art quantum devices, because they appear quite frequently. I think we are in the exploratory stage at this moment, so every idea is good. It's a matter of how do we utilize the knowledge that we've gained. So it's not about getting performance or getting better accuracy if we are doing deep learning and so on and so forth, right? It's more about how do we take that and then use it for other application? How do we use it for how general, what are the limits of the different technologies that we have today? All right.
Okay, another question. Hi, Professor. Do you have any easy on hand suggestions or principles of coding for DL or other MMM related applications that we should always keep in mind?
So number one, use a library that is already been optimized. That's the easiest thing to do. A lot of the common cases over the different years, and if you're talking about matrix multiply related stuff, over the several decades, a lot of the libraries have already addressed the common issue. So a lot of them are very well optimized, right? However, the problem is not with the libraries themselves, but how you are using the library. Very often the libraries make certain assumptions where they make certain simplification. Otherwise, the sheer amount of implementation they have to actually implement is a lot, right? So there are a lot of assumptions and a lot of constraints that are built in. Now, you need to be aware of them and that not use them blindly. But if you are writing it from scratch, then do what we suggest, right? Figure out what the hardware does well, use some of the models. There are many papers, including those from my groups, that actually says what are the models under different scenarios you should be using for DL or other MMM related applications. And those models are not very different from what we've described today in this talk, right? And if you use them, you should be able to implement them. The main thing is, if you want to write high performance code, if you want to write fast code, a lot of the ideas about modularity and abstraction, you have to be willing to step a little bit away from them, right? Because sometimes those actually hinders the techniques that are required for performance.
There's one more question. It is interesting to target the 𝗏, I'm not sure how to pronounce that. However, can you propose method work with GPUs? I am not sure if high-end GPU today manage the 𝗏 in the same way that you describe.
Right, so that's an interesting question, and it depends, and we could have a long discussion about this, but I'll give you my point of view and feel free to add to the question if you can. So GPUs have caches as well. They are organized as set associative caches as well, right? So for that reason, in principle, they should work. Now, what makes cache very different from, on the GPU, very different from the CPU is, on the CPU side, typically the number of ways are very limited. Whereas the number of sets on the GPUs are the limiting factor, right? And because they are different, you often have to write your code slightly differently, but to take advantage of the fact that the GPU can afford to hide the latency with more threads, more warps, and so on and so forth, right? But if you organize the threads accordingly, and if you, and let me go back to the earlier slide. Right, you see that using the same ideas, we can target the cache as well. Now, we may not be as accurate as we can be on the CPU because the caches are not as well explained or not as well explored as the CPU side, but we believe that that is definitely a possibility to do, because we do see that if you target the cache by associativity, and by the associativity, you do get something. Now, it's not exact, and we are working to actually improve our models so that it's more accurate on the GPU as well.
Okay, is there any other questions? Okay, there is one more. So one of the participants say it is interesting to target the cache. However, can you propose method work? Is that the same? Oh, it's just say thank you very much. So do you think one day CPU will be able to compete with GPU if we optimize the code better?
Right, that's an interesting question. It's not a matter of whether one day they will be able to compete. It's about finding the correct tool for the correct application. I believe that the CPU, with the correct application and implemented correctly, can outperform the GPU, but you need to find the correct applications and correct problem to use, right? At the end of the day, the CPU and GPUs are fundamentally very different devices targeting built on different concepts. So if you find a problem that favors one over the other, then that's when the CPU or the GPU becomes better, right? If you just compute raw performance for a large problem, then probably not. But if you find a problem that can leverage the capability of the CPU more than the GPU, then yeah, we don't need to wait for one day. I think we should be able to find some of them even today.
Is there any other questions? Any other questions? Last minute one. So I guess that is it. So thank you so much, Dr. Tze Meng Lo, for his inspiring talk. And thank you to all our participants for joining us today. Our next talk will be held next Monday, November 11th by Dr. Etiken from NVIDIA. He'll be talking about the future of AI in education. By the way, we're now accepting the fall 2021 Master and PhD applications with several scholarships being offered. So please check out our website or email us for more information. Thank you. I think we'll end the presentation here. Yes. Thank you very much, Dr. Tze Meng Lo, for joining us today.
Right. Thank you for inviting me.
Sure. Thank you so much.